Hello everyone, it's 11 o'clock, so I think we can start. Hello online people. Today we have also people in the room. I'm so pleased to hold this seminar here, hosted by Jan Monorazzi. We have a speaker from the University of Groningen. I hope you enjoy the seminar. If you have questions, you can ask them after the seminar, and those of you who are online, you can also write them in the chat, and we will also let you talk if you want to participate. So, Jan, all yours.
Good morning. Morning, everyone. Morning. It's my pleasure to introduce you Silvia Damerio from the Netherlands, from the Zernike Institute for Advanced Materials, University of Groningen. So Silvia is here visiting us this week. She obtained her bachelor degree from the chemistry department in the University of Genoa in Italy. Then she did her master degree in physical chemistry in the University of Groningen, and then she joined the mentioned institute for her PhD. And she's working under the supervision of Professor Beatriz Noeda. Then her research concerns the study of modulated phases, as you can see from her title talk. And she's going to tell us about the modulated phases of ferroic synchrones in calcium ferrite and barium titanate. And before inviting her, I would like to mention that she's a member of the American Ceramic Society and board member of WISE, so Women in Science and Engineering networking group at the University of Groningen. And so please welcome Silvia for your talk.
Thank you very much for the introduction, and thank you very much for having me here. Today, my talk will be about some of the work that I've been doing during my PhD at the University of Groningen, and as John already said, is about modulated phases of ferroic films. And all this work is done in the University of Groningen under the supervision of Beatriz Noeda. Okay, sorry. Here I can show you the outline of my talk. So just briefly, I will give a small introduction about modulated phases in general, and then I will focus on two example systems. The first are magnetic materials, so calcium ferrite. This is an antiferromagnetic material, and I will talk about the synthesis, the characterization of the films, and then some of the magnetic properties. I also work in my PhD on ferroelectrics, so I will talk about thin films of barium titanate, which is a ferroelectric and ferroelastic. And in my project, I also work on this iron platinum alloys. This is a mathematic system, and I will not discuss this in this talk due to time concerns. So just as a brief introduction, modulated phases are ubiquitous in nature, and we keep on seeing the same kinds of shapes and pattern all over in systems which are very different from a microscopic point of view, from the interaction that they have, but also on very different landscapes. So in this slide, you can see block polymers or polymer thin films, solid systems like ice, and again, magnetic systems or ferroelectrics, where you can always see this kind of modulations and pattern at different landscapes. So this indicates that there is a general mechanism that forms these phases, and the evolution of these phases under different external stimuli like temperature or fields is somewhat similar. And so we are interested on a general, on a fundamental point of view on this system. And in general, how do these modulated phases and periodic patterns arise? Usually they arise as a consequence of the presence of competing interactions. Here, for example, you can see some magnetic materials where we have different exchange interaction between the component spins of the system. In this case, where we have hexagonal lattices, for example, we can have spins which are coupled through a magnetic exchange, which is antiferromagnetic, and will tend to align all the spins in the lattice antiferromagnetically with each other. But due to the geometry of the hexagonal lattice, it's impossible to satisfy all the competing interaction and have all the magnetic exchange satisfied. So the result is a system where the spins will align in a 120 degree fashion because of the competition between these exchange interaction. And this happens all over in magnetic materials. For example, when we have chains of spins, like in this case, with different interaction between nearest neighbor and next nearest neighbor spins, what happens is that if these spins are free to rotate in the space, they will form some helical or cycloidal spin structure, while in, for example, Ising systems, they will create this periodic up and down chains in the case of the Ising. So this would be called the anisotropic next nearest neighbor Ising model, where we have these alternating spins up down in the ground state. But modulated phase can also arise at a larger scale, for example, between domains, when there is a formation of domains in films. And this again arises from the competition of different forces. We always have some anisotropy that can be the anisotropy of the magnetic material or the shape anisotropy induced by the growth on the thin form. And then there are always the exchange interaction between spins. And in case of magnetic and ferroelectrics, we have the magnetizing and depolarizing fields, which will tend to break the system into domains. And then we have to consider the domain wall energy and the surface energy and the elastic energy. All these forces compete and bring to different modulations and periodic structures in the system. And in general, this has been studied first by Landau and Lifshitz, and then Kittel and Roethor also applied it to ferroelectric films. There are often laws which dictate the period of this modulated structure, and the period W scales usually with the square root of the thickness of the film, and this will come again later. So the first system I'm going to talk about today is this calcium ferrite material. It's an antiferromagnet with a Neal temperature of around 200 K. And it has uniaxial anisotropy. So all the spins here are pointing in the plane which is perpendicular to the board. There are 4 kinds of exchange interaction between the spins. And we have this J1 and J2, which are weak, and J3 and J4, which are strong. So essentially, it forms this armchair chains, which are running along the z-axis, and each chain is weakly connected to each other. And the reason for this is that the J3 and J4 interaction are between iron atoms, which are connected through oxygen. So this is oxygen mediated super exchange with a bond angle of about 180 degrees, which is antiferromagnetic strong. While in the case of the interchain exchange J1 and J2, this angle is around 90 degrees. So it's close to the threshold between antiferromagnetic and ferromagnetic coupling. And the result is that this material orders in 2 different magnetic structures, which has been found both. One where this exchange is positive, so you can see it here, and it will result in a modulated periodicity of 2 up, 2 down, 2 up. And another case where this antiferromagnetic exchange is negative, so yeah, it's antiferromagnetic, so the modulation here is double, so up, down, up. What is not very clear actually about the system is how exactly the coexistence of these 2 phases works. Because, for example, if we look at neutron scattering data, we found that in in single crystals, A and B are found to both coexist down to the lowest temperature at the same time, while in other measurements which are done on powder samples, the B phase seems to only appear around the 150 K, while A seems to be the ground state at 5 K. So it's not clear if this coexistence is a first order phase transition, if it's down to low temperature or only limited to a narrow temperature range. And in addition, there is in a narrow temperature range around 120 K, the appearance of a net magnetization. So if we measure MH loop, despite both A and B are technically antiferromagnetic, there is a net magnetization in the system. And this has been hypothesized that can come from antiphase boundaries. So if we look at domains of each phase, for example, here you see 2 domains of the B phase, the boundary between these 2 domains is actually the local structure of the A phase. So it has been hypothesized that the coexistence between A and B occurs due to the formation of a lot of this antiphase boundary, which also carry uncompensated moments. And this difference between single crystal and powder sample made us think that it was really interesting to study also films of this material, because strain has been considered as a possible cause of the difference of magnetoelastic coupling in the single crystal and the powders. So we decided to grow films of this material and study them from their magnetic point of view, which I've never done before. So the first part of the work was about growing these films, and we chose a PLD method. And so in brief, we made our own targets, and we, with the laser, we ablate the target and generate a plasma plume that deposits the material on heated crystalline substrate, and we anneal by cooling down from the high temperature. And we grew our films on titanium oxide substrates. And what we observe is that we can get quite thick and homogeneous films grown on titanium oxide. We mostly grew films in thickness ranging between 50 to 150 nanometers. So this would be the film. And what was immediately evident when we cut these samples to observe in the cross section is that we have a native calcium titanate layer that forms at the interface between titanium and the film. So this is a reaction of the calcium with the titanium oxide, and you can see from EDS measurement that there's no iron in the intermediate layer, it's just calcium, titanium, and oxygen. So after this, we characterize our films by means of XRD. So this is a normal out-of-plane theta omega scan, and you can see a clear film peak appearing at about 33.5 degrees. Interestingly, in the crystal structure of this material, this peak could be attributed to two different crystallographic orientations. So from these measurements only, we couldn't exactly tell what was the out of plane of our film, either 001 or 302. So we perform more measurements, but before that, we also just look at the sample of the surface of our samples by means of AFM. And what was immediately clear is that the main structure of this material was not super simple. It was actually formed by at least 3 different in-plane orientations. So the film is composed by these elongated needle-like crystals, and all of them come into 3 different in-plane orientation. Here you see 1, 2, and 3. And by different measurements, so for example, this is a XRD4 figure, we could indeed see that these 3 peaks correspond to the 3 in-plane orientation of the crystal. And by electron rescattering diffraction in LCM, we can actually look at each individual domain and figure out how it's the crystal oriented locally. And these are maps that show the out of plane in the first case and the in-plane orientation of the crystals. So it's absolutely clear here that both of the 2 out of plane orientation that correspond to the peak at 33.5 are present. So the film has a mixed out of plane orientation, and each of them come with these 3 in-plane variants. So there are actually many structural domains in these films. And of course, the first question that came to our mind is, why does this even happen? And to understand this, we have to look at the structure of our intermediate calcium titanate layer. So in the TM, we can really see that the interface between titanium oxide and calcium titanate is quite ordered. We can see that for 6 columns of calcium titanate, we have 7, for 6 columns of titanium oxide, we have 6 of the calcium titanate, which orders in a perovskite structure. But then, if we look at the interface between calcium titanate and calcium ferrite, we can make a sketch of how this surface will look like. So in black, you can see here the atoms belonging to calcium titanate, and colored the atoms, the cations of calcium ferrite. And there is a pretty good matching of these atoms with both an in-plane orientation corresponding to domain type 1, but also when we rotate this of 55 degrees, which would correspond with the diagonal of the in-plane of the calcium titanate. So what's happening is that calcium ferrite is growing, forming islands which match the epitaxial relationship with the calcium titanate. And here, for example, in the TM, we can see the calcium ferrite crystal layer from 55 degrees from the in-plane orientation with the calcium titanate. So once we have these films, even though they are not perfectly single crystalline, we can already start studying them from the magnetic point of view. Because what is actually interesting is that for all this in-plane and for all this in-plane orientation, the magnetic easy axis, which is the B axis, would be along the long side of the needle crystal. So what we can do is first measure the magnetic properties along when most of the crystal is oriented with the B axis parallel to the magnetic axis in the squid. And what we see is that you can see here a plot of the susceptibility as a function of temperature. And there is mostly one magnetic transition at around 185 Kelvin. And there is this very characteristic large splitting between the zero field cooled and the field cooled curves. And this usually indicates some irreversible process. It's something that is typical of spin glasses, but usually the splitting temperature is much lower. It is not the nil temperature. While here we are already splitting at a nil temperature, if not even higher. And then we observe a maximum of the susceptibility around under 20, under 30 K, which is also where we have this opening in the MH loss. So the behavior macroscopically is quite similar to bulk, but we definitely only see one characteristic nil temperature magnetic transition. And when we apply the magnetic field perpendicular to the easy axis, we see that this shape is maintained, but much down. So indeed, there is an anisotropy in the system. And applying higher fields kind of saturates all our sigma. And we can also measure MH loops, and what we see is the same as or similar as in bulk. So with loops which are mostly closed for most of the temperature, but around under 30 K, we observe this opening and this magnetic hysteresis. And another interesting feature is that if we measure these loops by positive field pooling or negative field pooling, we can have a vertical shift of the loop, which usually it's quite unusual. Usually there are more horizontal shift when you have when you have coupling between an antiferromagnet and a ferromagnet, but here we also have a vertical shift of these MH loops. So we wanted to know more about the magnetic properties of the system, and having thin film samples allowed us to also perform some local characterization of the magnetic properties. But before that, we sent also our sample for Mossbauer spectroscopy measurements. So for people who are not familiar with the technique, it's a technique which is based on spectroscopy of the nuclear levels. So here we have an atom with a species that needs to be sensitive to Mossbauer. So we use iron 57 enriched samples. And iron, usually the way it works is that the nucleus absorbs the radiation, and when the atom is free without any nuclear environment, we will only observe one peak, which is at the horizontal shift, which is characteristic of this atom. But then when the atom, in this case iron, is in some kind of chemical environment, the peak will be shifted. First, it will have a shift which corresponds to its oxidation state. And then it's possible that it has also splitting due to its chemical environment. So this is called quadrupolar splitting, and it depends on the presence of some anisotropy in the bonding environment. And then when the material orders magnetically, we can also have a splitting which indicates the presence of long-range magnetic ordering. And we performed this experiment on our samples, and what we saw indeed is that we have two iron environments, so iron 1 and iron 2, and these are the two iron in the crystal lattice of calcium ferrite. So this was already telling us that there are not other iron-containing impurities in our films, and their shift in terms of horizontal shift correspond to iron 3+. So we also know that most of the iron here is the 3+ oxidation state, which is also a good sign, because in the case of oxygen vacancies, which are quite common in oxide films, we would have some iron 2+, while here, at least it was not detectable within the limits of the Mossbauer technique. And then we observed that there is indeed a magnetic splitting upon cooling down, and we see that it occurs at temperature between around 180 K, which is consistent with the squid measurements. And what we can do following these experiments is also plot the order parameter, which in the case of Mossbauer is the magnetic hyperfine field splitting. And plotting it, we can kind of follow the order parameter across the transition. And what we find is that this follows a power law with a critical exponent, which is close to 1/3. That is what we expect for a critical transition of an Ising system. So this is consistent with a critical single transition of a system with uniaxial anisotropy. And this is something that has not been shown for the crystals, single crystals. So at least we knew that in our films there was mostly one phase and it was ordering with a second order type transition. And then what we did was also investigate microscopically the properties of these films. So we have this interesting MFM instrument in our lab that allows us to measure MFM at low temperature. So we can first measure the signal, the magnetic signal above the needle temperature, for example, 200 K. And as you can see here, there's almost no contrast in the phase of the AFM. But when we cool down below the ordering temperature of this material, we can actually see some magnetic signal coming out. And now you can probably argue, but you just said that the easy axis of this material was in the plane of the film. So how do we actually see some MFM magnetic contrast, which is usually only out of plane? And the reason here we think is that we are picking up the stray fields, which are at the end of this individual crystal-like domain. So you can imagine to have the magnetization pointing along the crystal, and when we come close with the MFM, we can see the stray fields coming up at the end. So if you look at this image, there is quite some correlation between the end of the needle crystals and the magnetic contrast. And to verify this, we can also do these measurements inside an applied field, which is low enough to not revert the magnetization of the film, but actually reverse the magnetization of the magnetic tip in the AFM. And if we reverse the sign of the field, we get the opposite contrast in the MFM image, which means that now the tip and the films are coupled with a ferromagnetic or ferromagnetic change. So this was quite interesting because it was confirming our idea of this magnetic anisotropy along the easy axis, and also that indeed there are these chains of spins along the crystal needles. And the next experiment that we decided to do on these films, which gives quite a lot of information indeed on the magnetic anisotropy and the magnetic properties, are some spin hole magnetoresistance measurements. So these are more spin transport measurements, and I will now explain briefly how they work. They are based on the spin hole effect. The spin hole effect is an effect that occurs in metals with a large spin orbit coupling. So when we have a current going through the metal, the carriers, here in this picture it would be JQ, the carriers, the electrons in the current will actually scatter to different sides of the metallic conductor depending on their spin. So electrons will spin up, will accumulate to an interface of the metal, and spins will spin down to the other interface. So this generates a spin current, which is perpendicular to the charge current. And at the interface, we generate a spin accumulation, and the direction of the spin accumulation is again perpendicular to the spin current. Now, if we put a metal like this, for example, platinum, in contact with a magnetic material, the spin current can be injected into the magnetic material. And we will have injection if the direction of the spins at the interface is perpendicular to the magnetization. So in this case, the spin current will be injected into the magnetic insulator, and this thus will result in a higher resistance measured longitudinally in the metal. And on the other hand, when the magnetization in the magnetic insulator is perpendicular to the direction of the spins at the interface, we will have another spin current injected because of the inverse pinhole effect. So this will result overall in a low resistance state in the metal. So if we now start measuring the the resistance in the metal with the magnetization of the ferromagnetic layer or the magnetic layer rotating, we can have a dependence of the resistance on the angle at which the magnetization is pointing. And this is quite well known from a theoretical point of view, and the observed result is a modulation of the resistance that goes with the double of the angle alpha of the magnetic field. Now, all of this works for longitudinal resistance, as I was saying, but actually we have a modulation also when we measure in transverse geometry, and this will have a 45-degree shift with respect to the longitudinal one. Now, if this magnetic layer is not a ferromagnet, but it's an antiferromagnet, something slightly different happens. So here, if we apply a field which is large enough to have a spin flux transition in the material, we will have that the near vector is always pointing perpendicular to the applied magnetic field. So the result is an SMR which looks the opposite of the ferromagnetic one. So it has a negative sign in front of it. And conventionally, this is called negative SMR and has been seen in different antiferromagnets like iron oxide or nickel oxide. So we wanted to try to measure this to figure out the direction of the easy axis and how possible it was to orient it with the magnetic field. And just to give you an example, this can be measured also in different planes. And when we measure in the in plane, we will expect to observe a modulation with under the 80-degree period. And when we can also measure this SMR rotating the field out of plane. And rotating the field out of plane will give different responses depending on which plane we are scanning. For example, in here you're seeing the magnetic field rotated in the plane between the current and the out plane. And this is expected to give no modulation because here the magnetization is always pointing perpendicular to the direction of the spin accumulation. So from the injection point of view, there's no difference here. But if we scan the magnetic field in the plane that contains the transverse directions, we are again expecting to see a modulation with two of the angles. So what we did to begin with are building larger hole bars, which can cover different of these crystallographic domains on our films and start to measure the spin hole magnetic resistance in the plane of the film. So here what we see is that when we start the low temperature, 5K, we observe a modulation with the sign of 2 alpha. And this modulation has the periodicity for a classic negative SMR, so what will you expect from an antiferromagnet? But upon increasing the temperature, this modulation first decreases in amplitude and then it reverses its sign. So at a larger temperature, we observe what is more similar to a ferromagnet or a paramagnet. So here you can see a plot of the amplitude as a function of temperature. And what was surprising for us is that this change of sign was not occurring at the nil temperature where the material is becoming ferromagnetic, but actually was occurring much lower at around 100K. And what was even perhaps more surprising is that we also saw modulation when measuring in the beta plane, which is where we expect the modulation for a ferromagnetic material, so where the magnetization follows the field. And also we saw a modulation in the other plane, where for a normal ferromagnet it was not expected to have. And this modulation decreases in amplitude with temperature. So what we are seeing here is that there are actually two components to this in-plane SMR signal. And one is a positive component, more ferromagnetic-like, and one is the antiferromagnetic component from the longer range ordering. And what we also did, because our first question was, can this arise from imperfection and defects that we have at the interface between all these crystallographic domains? And what we did then was build very small hole bars, specifically addressing each individual crystallographic domains. And what we see here is that the SMR is always positive. So it's even different from what we would expect here. So the sign here is always positive, which means that the ferromagnetic contribution in these smaller hole bars is larger, but the trend is always the same as the larger bars. So what we see is that we have this antiferromagnetic component, which is stronger at low temperature and then decreases as we approach near temperature, but the positive component is always there across the whole temperature range. And if we look at the field dependence of these two components, none of them saturates with fields as attractive for a ferromagnet. And they scale, one of them scales linearly, so the positive one scales linearly with the field, which is consistent with paramagnetic or at least non-interactive spins. And the antiferromagnetic component scales quadratically with the field. So this is telling us that we have indeed this antiferromagnetic component, and in addition, a component which looks like from non-interacting or uncoupled spins. And so what we learn is that these non-interacting spins can very well match with what reported from the spins at the antiphase boundaries of the calcium ferrite. So we can grow thin films of calcium ferrite by means of phosphorylated deposition, and the structure of these films follow epitaxially the structure of the substrate and is mediated by this calcium titanate layer at the interface. And macroscopically, we observe that there is a single magnetic transition. So differently from somewhat single crystal sample, we only have one ground state that orders through a second order critical transition. And we also observe that there is two components in this ordering, an antiferromagnetic component and a component of these uncoupled spins. So what we think is that these uncoupled spins at the antiphase boundary are usually non-interacting because the antiphase boundaries are quite far away from each other. And what happens is that close to the near temperature, so close to the critical temperature, there are longer range interaction which allow the spins to interact together and generate some net magnetization in the system. Now, the other system that I would like to talk about quickly, hopefully I will be fast, it's barium titanate thin films. Barium titanate is a peroxide ferroelectric, which orders in this trigonal phase. But when it's grown in film form, due to the misfit strain with the substrate, we can induce the formation of different phases. And these phases are phases in the term of domain structures. So what I mean is that, for example, when we are in a regime of low misfit strain, for example, here blue and red, we can have phases where the polarization is pointing in some domains in plane and in some domain out of plane. So this, for example, would be AC kind of phase. And otherwise, at a lower temperature, we have this other phase where in all the domains, the polarization is always pointing in plane in the film. And this would be AB type ferroelectric phase. And what is interesting is, of course, that because this is ferroelectric and ferroelastic, we can measure and characterize which phase it is in by means of Kaiser response force microscopy. So what we did with these films is grow a barium titanate of neodymium scandate substrate, which induce a very low compressive strain. And we can assess the transition between this in-plane and alternating in-plane, out-of-plane phase at a reasonably low temperature. And we follow this phase transition by means of this response force microscopy. So here you can see how it looks in the piezo response force microscopy, the two phases. So this would be the room temperature phase, which is AB, and the domain here are aligned along the 110 direction at 35 degrees. And when we warm up across the phase transition, we switch to the in-plane, out-of-plane phase. And now the domain walls are at 45 degrees with respect to the domains of the other phase. So we see a tilt in these domains. And of course, if we go above the ferroelectric phase transition, then the apparent contrast disappears. So the first thing that we can do is also measure the periodicity of these domains as a function of the thickness of the films. And what we expect, as we saw in the introduction, is a periodicity that scales with the square root of the thickness of the film. And indeed, this is what we found in the A phase and the AC phase, and we have this prefactor parameter of about 10. And this depends on the properties of the material. So in general, it's expected to be the same in all the phases of the same material. But what is interesting is that when we measure the high temperature phase, not from cooling from the ferroelectric phase, but upon heating from the low temperature phase, we find that this pre-parameter is now decreased to 7. And this is due to the fact that the domains of the new phase actually form on top at the position of the domains of the low temperature phase, because that's easier to nucleate in the pre-existing domain position. And this induces a geometrical constraints to the periodicity of the higher temperature phase, which is thus actually linked to the low temperature phase. And what we can do is also really measure the phase transition following it through the cooling process in the PFM, because this is quite a slow phase transition. And what we observe is, for example, when you cool down from the high temperature phase, we start having domain of the low temperature phase with a certain periodicity, and the new domain walls will nucleate exactly in the middle of the pre-existing domains. And the phase transition will occur through these sequential periodicity doubling events. And the same happens when we measure upon heating up. So we start with a certain periodicity, and then the domains disappear upon period doubling cascades. And we also see a certain hysteresis in this transition. So it means that upon heating, upon cooling, the temperature are not exactly the same. So this is classic example of first order phase transition, where we have a coexistence of the two phases and over a broader temperature range, so not a critical transition. And what we also see is that upon giving the system some time to relax at each temperature, wherever we have some defects and some wrongly, let's say, wrong periodicity due to domain spin by defects, we see that a relaxation occurs, and then the equilibrium periodicity is achieved after some time. Only in the case the defects are not too big. So when we have something like a huge particle, the domain just gets spin there, and the periodicity is not received. So in conclusion, we have shown that the transition between these phases of titanate occurs through sequential period doubling events, which is quite a general mechanism and is quite known in the dynamical system as a route between disorder and chaos states. And if we look at the literature and we look at more of these ferroelectric materials, but also other kind of materials, we found that domains with sizes which are related by this 2 to the power of n rule are quite common. And this might indicate that it's a general mechanism, not only for this specific system. And finally, measuring these films with other methods has shown that there is a very high dielectric response on this material, which is temperature independent. So this means that this coexistence between different phases and different periodicities can actually help to make the material more sensitive to external stimuli and can be used for devices or in general applications. And with this, I would thank all the people in my research group, so nanostructure of functional oxide, specifically my supervisor, Professor Noheda, Dr. Pavan Nukala, which was a PhD in our group and with the TIAM experiments, and Dr. Vazek Ochelik, which helped with the EBSD measurements, and other collaborators from France, which helped with the Mosbauer experiments, and in the F&D group of our institute, our collaboration for the transport experiments. And in the work of on barium titanate, I want to thank Dr. Arnaud Everard, which was a previous PhD in the group, which drew the films, and our collaborators at ICN2, Nes Domingo, Gustavo Catalan, and Professor Ekel Sadie of the University of Cambridge. And of course, thank you very much for inviting me here, Professor Janapchi, and thank you very much for your attention.
Hey, thank you, Silvia, for this comprehensive talk. So we can take questions now. either in the audience or Zoom online. I can start with one. So you said in slide 11 that you also see kind of
a long time. I don't know.
change bias.
Yeah, the vertical shift.
The vertical shift, yeah. Then you didn't give like a mechanism to explain it. You said that this is interesting. It's not typically what happens when you cool a system. So what do you think is happening in this?
Yes, what we think is that there are indeed these two different ordering. So there is a long range antiferromagnetic ordering, and then these spins at the antiphase boundaries. And when we apply a certain field, can be positive, the spins at the antiphase boundaries orient with the field. And so they preferentially stay oriented like this. So when you feel cool, then you will have this extra net magnetic moment due to the spins. And then so this would induce a vertical shift in the positive direction. While if you feel cool with a negative applied field, the antiphase boundary will be preferentially oriented negative. Why we also don't see an exchange bias in the horizontal direction, so why are the looks way less shifted in the horizontal is probably because the spins are really free. They are not coupled to the antiferromagnetic order parameter, and that's also consistent with the linear dependence on the field on the SMR measurements.
Okay, so those spins basically cannot be manipulated with so small fields. So do you expect like a much larger field that they would eventually align with the external field?
I think so, because from the SMR we already are applying quite high fields, but still it's always linear. We don't see it saturate ever. So we probably need a higher field than what we could apply in our lab.
Thanks.
Thanks for your talk. In the introduction, you mentioned from neutron scattering experiments about this discrepancy between powder and zinc crystals regarding the possible, what we call it A or B possible spin orientation. So, in the light of your experiments, what can you say about that in your film?
Yeah. So in the light of this, I think what we can say is that for sure, one of the two is only the ground state, at least in the films. So it's not, this system doesn't have two ground states. One of them is the ground state that forms at the nil temperature, and the other one comes from the formation of these antiphase boundaries. What we want to do is also do neutron scattering on the films to actually verify that this is true also for the films. But the idea, what is the general understanding, is that the system tends to order in the ground state, which is the B phase, and then the A phase forms due to all this antiphase boundary in the B phase. And actually, when there is some strain, for example, in the case of powders, which are usually obtained by grinding the single crystals, the strain stabilizes the A phase, which is the metastable non-ground state. So our idea here is measure also neutron scattering in the films to actually verify that is the case, the same case in the film films. So since here we don't have any specific strain from the crystalline substrate because it's forming all these domains that allow the structure to relax, we also expect to only see that both phases are present down to low temperature because there's not this stabilization of the A phase strain.
These phases are incommensurate with the.
No,
in neutrons they give satellites or.
That I know, they are commensurate, so they see very specific peaks belonging to one and the other because they don't have the same vector orientation. I'm not an expert of neutrons, but I can probably. Yeah. here. So they can, here they're plotting the intensity of the peak in the neutron experiment. So they can follow the 102 peak to follow the B phase and the 101 peak for the A phase.
Yes,
So
so it's good.
yeah, there's no shape.
The question here.
Thanks, Silvia, for the presentation. I have a couple of questions which I'm not sure if they are related or not. The first one is regarding to the growth. I think that you have identified the presence of a phase which is strong calcium titanate. That is quite thick. Your layer is a few nanometers, maybe 20 or 30 nanometers, so
10 nanometers.
or 10 nanometers, so it's not
Yeah.
1 nanometer. So that means that during the growth, you should have an excess of iron. And iron gives a huge magnetic signal in this measurement. So all magnetic measurements should be somehow affected by the presence of a big amount of iron. No, big amount, no, the big signal from iron. Where this signal appears in your magnetization loops and in your most valuable.
So we think that there is not this extra iron because especially Mossbauer is really sensitive to all the iron species. So we don't see any metallic iron atoms in our signal. We only see the two iron positions that belongs to the iron in calcium ferrite. So what we think is actually that the problem here is during growth. So there is not a perfect stoichiometric transfer of the stoichiometry of the targets to the films, and we are losing, especially at the beginning of the growth, some iron. And the reason for this is that when we look at our targets after the growth, especially when we grow at lower laser fluence, we have some redeposition of iron, and we have this smaller iron island on the sample. So what we think is that, especially at lower fluence, we can't ablate iron and calcium at the same rate, and we actually have some iron which is remaining in the target. And then, so overall, the stoichiometry is not exactly the same, so we have this iron deficiency at the interface. And we also perform XPS measurements to also try to be sure that the stoichiometry of the films didn't have any iron 2+ or other iron in metallic form, and we could never see it. So we think that actually there is not extra iron in the film.
In fact, if you show the slide of the magnetization along different direction,
Yeah.
this one, you do see that between 400 kelvins and, let's say, 200 kelvins, during 200 degrees, you have a big hysteresis that you should not expect, I guess, I don't know, antiferrometric material ordering at 120 or 180.
Yes.
It's a huge hysteresis.
Yes, that's true. And this is also was also our, of course, concern. Why is it staying like this? And it also was found in the literature in other kind of samples that there's often a bump in the susceptibility above the mean temperature, and they believe that this is due to short range correlations between the irons which remain up to higher temperature.
In the Mossbauer, why this iron 1 component is asymmetric in the?
Yeah, in the.
I mean the intensity.
Yes. So I think the shape of the quadrupolar splitting depends on the shape of the octahedral environment, because the quadrupolar splitting is linked to asymmetries in the electric field environment of the iron. So if the iron is in octahedral environment which is distorted and not perfectly symmetric, gives rise to the splitting. And I think that the difference in the amplitude is related to the asymmetry in the octahedral environment of the iron atom in the structure.
Okay, Can I comment on that?
Yeah.
Well, to the question of Martia, if you take polycrystalline sample, you have a
This is because it's
polar splitting, it should be symmetric.
okay.
It is a polycrystalline sample, but if you have a single crystal or film, whatever, then the ratio between intensities, depending on the direction of
The gamma rays
with respect to the tensor that gives you the quadrupole splitting, which is the tensors of the diagonal of the tensor. And in fact, here, for some reason, one of the components gives a similar intensity and the other different intensity. In fact, this angle tells you which is the direction between the axial direction of the quadrupole splitting and the gamma ray. So from that, one should be able to know if one is like that and the other is with respect to the gamma ray. So I don't know in that case how it works, but in general.
Another question? Anna, do we have any question online?
No.
Okay. And well, let's thank Silvia again. And yeah, I would like to mention that she is going to be here until the end of the week. So if you want to have any discussion one-on-one about her research, then please contact me or her. Then you see us at home. So yeah, thank you again.